Hey everyone, Morgan here. So we're going to do an answer key for the worksheet on electromagnetic radiation number 2. And there are two numbers which we're going to use over and over again today, which are the speed of light and Planck's constant, both that are provided, and they'll always be provided for you, so don't worry about trying to memorize them. So a microwave has a wavelength of about 1.0 centimeters. What is the frequency of one photon of this radiation? Well, I'm going to start off by getting it out of centimeters times 100 centimeters to 1 meter, which gives us 1.0 times 10 to the negative second meters, because centimeters cancels. So there we go. Much more convenient unit for us to be working in. Now I know that C equals lambda times nu. I know lambda, I'm looking for nu. Nu equals C over lambda. And this equals the speed of light, which is 3.00 times 10 to the 8th meters per second, divided by 1.0 times 10 to the negative second meters. Meters cancels meters. And when I run this through my calculator, I get 3.0 times 10 to the 10th 1 over seconds. And I know some people like to write hertz, HZ, but I still like just to write it as 1 over second. Okay. Second question, what is the energy of this photon? Well, we know that E equals H nu, which equals H is given 6.626 times 10 to the negative 34th joules times seconds, and that is going to be multiplied by the frequency, which was 3.0 times 10 to the 10th, 1 over seconds. The seconds are going to cancel, and this comes out, or rounded off, as 2.0 times 10 to the negative 23rd joules. It's only one photon, so that's not a whole lot of energy, okay? All right, so now, some red light has a wavelength of 675 nanometers. What's its frequency? Well, let's get it into a convenient unit. 675 nanometers times, and we know there are 10 to the 9th nanometers in 1 meter, which equals 6.75 times 10 to the negative 7th meters. Okay, if C equals lambda times nu, nu equals C over lambda, which equals 3.00 times 10 to the 8th meters per second over 6.75 times 10 to the negative 7th meters. Meters are going to cancel, and I end up getting 4.44 times 10 to the 14th 1 over seconds. Okay? And as always, you could call that hertz, H-E-R-T-Z. And the energy of that photon, E equals H nu, will equal 6.626 times 10 to the negative 34th joule times seconds, multiplied by the frequency I just got here, 4.44 times 10 to the 14th, 1 over seconds. Seconds cancel seconds. And this equals 2.94 times 10 to the minus 19th joules. And again, you know, a photon is really small. It's not going to have a whole lot of energy. That's why these are such small numbers. Let's not worry about that. Okay, so now, a radio station is broadcasting at 100.3 megahertz. 100.3 megahertz, that would be an FM station, times 1 megahertz has 10 to the 6th hertz. So megahertz cancels. And this actually comes out to be 1.003 times 10 to the 8th hertz, which I'm just going to call 1 over a second. Now, C equals lambda times nu. We know nu, so lambda equals C over nu, which is 3.00 times 10 to the 8th meters per second, divided by 1.003 times 10 to the 8th, 1 over second, so second ends up upstairs this time. Second cancels seconds, and this comes out to be about 2.99 meters. Okay, that's the first page here. I'm going to go back up here for a second. Try and line that up for you. Question number 1 and 2, if you need to relook at those. Pause if you have to. Then we'll go down here. Questions 3, 4, and 5. Let you take a look at those. Okay, so now we'll go over to the back page. What is the energy of one photon of the radiation in question number 5? So E equals h nu, which equals 6.626 times 10 to the negative 34th joule times seconds. We're going to multiply that by the answer for frequency, 1.003 times 10 to the 8th, 1 over seconds. And the seconds are going to cancel. And this comes out to be 6.646 times 10 to the negative 26th joules. Okay. It's radio wave. It's really low energy. Okay, so we have a television remote control. It operates on a frequency of 38 kilohertz. What is the wavelength and the energy? So first off, 38 kilohertz times 1 kilohertz has 1,000 hertz, and that ends up equaling 3.8 times 10 to the 4th, 1 over seconds. Okay, so now for the wavelength. C equals lambda nu. Lambda equals C over nu. And that's 3.00 times 10 to the 8th meters per second over 3.8 times 10 to the 4th, 1 over second. Seconds cancel seconds. And this is about 7.9 times 10 to the 3rd meters. Okay? Now, for the energy, we know that E equals h nu, and h is given 6.626 times 10 to the negative 34th joule times seconds. And we're going to multiply by the frequency, which was 3.8 times 10 to the 4th, 1 over seconds. Seconds cancels seconds. It's about 2.5 times 10 to the negative 29 joules. Very, very low energy. Okay. Now, we got a British radio station, and it's identified by a wavelength of 3.14 meters. What is its frequency and energy? All right, we can do that. C equals lambda times nu. This time we happen to know lambda, so nu equals C over lambda, 3.00 times 10 to the 8th meters per second, and that is going to be divided by 3.14 meters. Meters is going to cancel, and this ends up coming out to be 9.55 times 10 to the 7th, 1 over seconds. Now, I just happen to recognize this. If I move the decimal over one, that's 95.5 times 10 to the 6th hertz, or what we might call here in America 95.5 megahertz, which here in Los Angeles, that is a station called KLOS. E equals h nu, which equals 6.626 times 10 to the negative 34th joules times seconds. I keep saying you don't have to memorize that. It's going to be printed on the test, and that's great. But you will have typed it into your calculator so many times, you probably remember it. 9.55 times 10 to the 7th, 1 over seconds. Seconds is going to cancel. And this comes out to equal 6.33 times 10 to the negative 26th joules. Okay. I put a lot of unit conversion into this homework because I wanted you to see the frequencies and the wavelengths as they would likely be listed in everyday life. Okay, we got a nice bright line in the hydrogen spectrum at 486 nanometers. So let's convert that 486 nanometers times 10 to the 9th nanometers for 1 meter, 4.86 times 10 to the negative 7th meters. Okay? If C equals lambda times nu, nu equals C over lambda, and that is 3.00 times 10 to the 8th meters per second over 4.86 times 10 to the negative 7th meters. The meters are going to cancel, and this frequency comes out at 6.17 times 10 to the 14th 1 over seconds. The energy, E equals h nu, is going to equal 6.626 times 10 to the negative 34th joules times seconds, multiplied by 6.17 times 10 to the 14th 1 over seconds. Second cancels second, and this is 4.09 times 10 to the minus 19th joules. Okay. Now, question 10, nice, straightforward. Frequency, 3.0 times 10 to the 16th hertz. So the wavelength, lambda equals C over nu, which equals 3.00 times 10 to the 8th meters per second divided by 3.0 times 10 to the 16th 1 over seconds. So seconds cancel seconds, and this equals basically 1.0 times 10 to the negative 8th meters. Now, I don't want the energy of 1 photon, I actually want the energy of 10 photons. Okay, it's actually not that different. We just say E equals nh nu, and n is our number of photons. So 10 photons times 6.626 times 10 to the negative 34th joule times seconds, multiplied by 3.0 times 10 to the 16th 1 over seconds. Seconds cancels seconds, and this comes out to be 2.0 times 10 to the negative 16th joules. There we go. All right, so let me scroll back up here for a second. Questions 1 and 2. You can pause the video if you need to. And now we'll go back down to here for questions 8, 9, 10. Okay, there you go. That is electromagnetic radiation number 2. Hope you're having a good day. Thanks for tuning in. This is Morgan signing off.